Hello everyone. I'd like to discuss balanced binary search trees, and then I'll present a data structure called an AVL tree which maintains balance. But first, what is a balanced binary search tree? So to get at this, I'm going to start with some code that we've been developing over time to draw a binary search tree and also to add things to it. So to get at what a balanced tree is, let me first make a perfectly unbalanced binary search tree. So to do this, what I'm going to do is I'm going to add a bunch of stuff in sequence. So I'll say, for example, for x in range 10, t.add x. And let's just look and see what that tree looks like. So here's the tree I get when I add 0 through 9 in that order. So first I add 0, that's the root. Then I add 1, 1 is greater than 0. Then I add 2, 2 is greater than 1. Then I add 3, 3 is greater than 0, 1, 2. And so what you end up making is a glorified linked list. And this is really bad because add and contains and remove, as we've seen, in the worst case, take time proportional to the longest branch from the root down to a leaf. So in this case, the branch is as long as there are nodes in the tree. It has as many nodes as there are trees. So what that would mean is that add, remove, and contains all take linear time in the worst case. And we want to try to avoid that. Okay. Now let me do something a little different. I want to show you kind of the best case that you can hope for in a balanced binary search tree. So what I'm going to do is I'm going to make an array of elements. I'll start off by making the elements in sequence as before. And I'm going to make a recursive helper method that adds them in a very particular order. So right here I added 0 first and then 1 and I added them in sequence. That was a really bad idea. Actually, you know what? I'm also going to go up to the number 15 here. We'll see why in a second. Okay, so let's say I added 15 things. And here we go. All right. So it was a bad idea to add these 15 things in sequence. But if instead I added the median first, so in this case 7, that's going to divide things in half, right? So that's good because that gives me hope that I can have kind of an equal number of things on the left and an equal number of things on the right. Problem here is that everything's on the right. So I kind of want to put an equal number of things on the left and an equal number of things on the right. So let me do that. So I'll make a method called add median. I'll pass along a tree and I'll pass along an array. And what I'll do is I'll say, okay, the index of what I want to add is the length of the array, 4 divided by 2. That's the median, assuming that the array has an odd number of elements. And then what I'll say is if actually, before I do any of this, I should make sure the length of the array is greater than 0. That's the base case. As long as there's still something in the array, let me figure out what the median is and let me add it. So I'll say t.add array at index I, and then I'll say, now I gotta do some recursion. So I'll say add median up to but not including I, and then add median at index I plus 1 to the end. And of course I need to pass along this t as a parameter. Okay. So let me call this method and see if it works. So if I were to say, okay, let's make a new tree, t is equal to binary tree, add median t array. Invalid syntax. I meant to say if, I was wondering why the tabbing was messed up. If the length of the array is greater than 0. Okay. So if I do this, here's what I get. This looks a lot better. So you can see that every level of the tree is full. What I mean is, okay, so we got the root, and then at the next level, so 1 down, I have a left child and a right child. And each of those have a left child and a right child. So then the level after that is full. And then finally, the level after that is full as well. And so let me go up now actually to 31 elements. I'll show you that this will continue, this pattern. And actually I can even make these random. I can say, all right, let's make this an mp.sort, mp.random.randint 0 to 1000, let's say. I want 31 of those. And as long as I sort them first and do this thing where I take the median and then recursively put all the things on the left, recursively put all the things on the right, I will end up balanced, except I guess I probably had a repeat value, so I didn't quite actually have 31 unique values there. Okay, so I will define a perfectly balanced binary search tree as a tree with every level full. And another way to say this is every internal node has exactly 2 children. All right? So definitely not true about this at all. Every internal node here has exactly 1 child. That's the worst case. Usually some will have 1, some will have 2. But this is the best case where everyone has 2 children. So if we look at that, we can actually learn something about how many nodes are there given a particular height of the tree. Okay, so first let me define what I mean by height. So the height of a node is the length of the longest path from that node down to a leaf. So here I'd say the height of 15, the height of the root here is 1, 2, 3, 4, right? But the height of this root here is actually 14, because that's how many steps I have to do to get down to the leaf there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay? So that's the height. So this height is clearly shorter than the other one. And so let's get a handle on, if this is totally full, how many nodes are there if the root has a particular height. So if the tree overall is a particular height. So given a tree of height h, we have how many nodes? So I'll say nh equals, well, we have the root, right? 1 plus 2 plus 4, and so we keep doubling each time, right? And then eventually we go up to, okay, so here I've got a height of 4, and then this bottom level here has 16, if you count. So this is 1 plus 2 plus 4 up to 2 to the h nodes. All right? So that's how many there are. All right, so we check this here. A height of 4, that would be 2 to the 5th, which is 32 minus 1. And there we go. We packed in those 31 nodes there. So I can ask the question, okay, if I have a certain number of nodes, what would be the height of a balanced binary search tree with packing that in? And so to get that, what I have to do is take this equation and solve for h. And so if I move things around a little bit, what I'll get is that h plus 1 is equal to, so I got to add this 1 over here and then take the log base 2 of both sides. So that would be log base 2 of n plus 1, right? And so then, I'll move that plus 1 over the other side. So I'll say this, all right? So the height of a balanced binary search tree would be that. And what I notice about that is that h is big O of log n. And so this means that add, contains, and remove all take logarithm of time in a balanced binary search tree. So that's great, because this really controls the length of the longest branch from the root and make sure it's not too long, and so we can keep these operations efficient. So that's what we want to aspire to. Okay, now I want to talk about AVL trees. But before I do that, let me give you a way to define heights recursively, which will help us to reason about AVL trees. So let's say I had this tree here, and if I pick out node 10 here, I can look at this and I can say the height is 4. And that's because this is the longest branch here. I go 1, 2, 3, 4 steps to get to that leaf node. But there's actually a way to define it which is a little bit easier to work with, by defining recursively based on the heights of its children. And so what I would say is, okay, the height of a particular node is the max of the height of its left child and its right child, plus 1. Okay? So I look at that example 10. The height of its left child, okay, this is height 2, right? And then the height of its right child is 3. 1, 2, 3. And then I have to go one additional hop to get to that node, right? The node pairs the two things together, and so that's an additional hop. So whichever one of these is bigger, in this case it's the right child, whichever one has a higher height is the one that I can construct the longest branch on. I just add one additional hop here. And then I also have my base case that if the node is a leaf, then the height is 0. And actually, if the node is none, the height is -1. And the reason I need that is because, let's say I wanted the height of 13. Well, the 13's right child is -1. That has a height of -1. And so I just need to be able to define the height of something that's not there. And actually, that would tell me also, that would imply that the height of a leaf node is 0, because both its children have a height of -1, and -1 plus 1 is 0. So it's probably enough to say this, but I like to also explicitly say that if the node is a leaf node, the height is 0, because I just want to remind you that's how it works. All right, let me encode this definition in our tree class. So what I'm going to do is make a recursive method that uses memoization to compute the height of each node. And that'll help me out here. So maybe I'll say that the height is equal to, I'll make some value called undefined. I'll make it -2, because the height could never be -2. So I'll say, all right, the height is undefined by default. But I'll have some method called compute height. And what I'll do is if self.h is undefined, then I have some work to do. I need to use my recursive definition to compute the height based on the height of the children. And so what I'll do is I'll say, okay, let's first figure out which child has the maximum height. And so I'll say, okay, so max h of a child. I'll make that be -1 to begin with, right? If it has no children, then the max height is -1. So let me check the left one first. I'll say if this actually happens to have a left child, then I'll say, okay, max h is equal to, whoops, I meant to write left, self.left. Max h is equal to self.left.compute height. And so actually at the end of this, I will return self.h. All right, so if there's a left child, let me see what the height is on the left. If there is a right child, then I'll say max h is, I might actually be higher than the left child, so I'll say the max between what I've seen so far and oops, I meant to say self.left.compute height, and then self.right.compute height. And once I've figured out what the max height is between them, then I can finally set, this is the memoization, I'll set my height to be max h plus 1. All right, so that's my definition. So let me go ahead and actually add the height to my plot here. So I'll plot the height as that. And okay, so now I'm ready to update this tree class here. So I'll do that. And okay, that was my perfectly unbalanced search tree. I've got to actually compute the heights though. So once I add all the nodes, let me say t dot, and I guess I should have an entry point here. So assuming that I've added a bunch of things and this is fixed, I can have an entry point here that says def compute heights. And so I'll say if the root exists, then I'll say self.root.compute height. And that will branch out and compute and memoize all the heights. All right, so let me do that now. So I'll say t.compute heights. All right, and so here we get exactly what I said before. So the height of the whole tree is 14. And you can see how it goes down in that descending mode there. On the other hand, the heights here, whoops, I got to compute them. So say t.compute heights. Whoop. So the heights here turn out to be, it goes 0, 1, 2. And so the height of the whole thing is 4, just as I promised. Now it's getting a little messy down there. I'll clean that up before the final notes. All right, so anyway, just wanted to have that recursive definition in hand. All right, so fix things up a little bit, and this is how I'm plotting the height as something in a parentheses here. So I'm finally ready to define an AVL tree. So an AVL tree is a binary search tree where the difference between the heights of a left child and a right child are always within 1. So I can say it like this. So I can say where the absolute value of the height of a node's left child minus the height of a node's right child is less than or equal to 1. All right? So the heights of the left and the right children differ by at most 1. Okay, so the balanced binary search tree that we have is definitely an example of an AVL tree. Because every node has a left child and a right child that have the exact same height. So this is kind of the best case. But the AVL tree lets us get away with a little bit more. So it's a little bit more permissive. You do not have to be perfectly balanced on the left and the right, but you can't have a height difference of more than 1. So let's try to think about the worst case that's allowed under there. So let me try to leave as many gaps as possible in the different levels while still respecting the AVL condition. So if I start with a tree with just, a single node, that's kind of the trivial example here. But what if I was going to make an AVL tree that had a height of 1 with as many gaps as possible? So that would look like this. And so actually, let me catalog them by their height here. So this height here is 1, or 0 actually. And the height of this tree is 1. Okay, now let me make a tree that has a height of 2. That leaves as many gaps as possible. So what I'm going to do is I'm always going to start with the root. What I'll do is I'll put the heavier tree on the left, so I'll put the tree with more height on the left, and then I'll put the tree with a smaller height on the right. And so that's the tree I get. All right, so notice at this node, height of left child, 1. Height of right child, 0. So they differ by 1, but not more than 1. If I were to add a node down here, then this would break the AVL condition, right? Because the height of the left child would now be 2, and the height of the right child is 0, and that's a difference of more than 1, okay? So you can't have a difference of more than 1, but this is okay. All right, so let me keep going. Let's say I wanted a height of 3. And so I'm going to keep following this pattern here where I start with a root and I take kind of the biggest tree I can with a height 1 less than this. I'll put it on the left. And then I'll take the smaller tree and put it on the right. I guess for aesthetics, I will flip this horizontally. All right, so let's see, can I get this arranged here? So here's my tree of height 3. And maybe I'll just do one more to hit this point home. So my tree of height 3 looks like this. And let's make a tree of height 4. And to do that, I'm going to start with a root. And I'm going to put the big one of height 3 on the left. And then I'm going to put the one of height 2 on the right. And I guess again for aesthetics, I will flip this horizontally. But the important thing is, I don't know, actually, no, yeah, that's good. But yeah, the important thing is you can see I'm doing this kind of recursive pattern here, where I say, okay, take the last 2 kind of bad trees that you made, or the worst possible trees that AVL allows you to make, and glue them together to root. And so you see, there are some gaps here, right? So in this tree, okay, I filled the root, I filled this level, I filled this level. But this level is supposed to have 8 things in it. It only has 4. This level is supposed to have 16 things in it. It only has 1. So how many things am I actually packing into these heights? So at a height of 0, I have 1, right? At a height of 1, I have 2. At a height of 2, I have 4. At a height of 3, I have 1, 2, 3, 4, 5, 6, 7. And at a height of 4, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And so this is part of a more general formula that we can look at, where we can say that the number of nodes, kind of the worst case, the fewest number of nodes that you would be storing in an AVL tree is equal to, so yeah, let me let NH here be the fewest number of nodes that you could possibly store at a particular height. Now I know I could do better than this, right? I showed you a moment ago at a height of 4, I should be able to get 31. Here I can only get 12. So I'm not using all the capacity that I would for a perfectly balanced tree, but let's reason about what the worst would be. So in the worst case, I would say, okay, NH is equal to NH minus 1, right? Plus NH minus 2 plus 1. So I take the worst tree with h minus 1 nodes, put that on the left. Take the worst tree with h minus 2 nodes, put it on the right, and then glue them together at the root. And so that is the relationship. And so if you look at this, this looks an awfully lot like the Fibonacci sequence. And so it turns out you can actually bound this with Fibonacci numbers. But I'm going to come up with a slightly simpler bound that allows me to prove that this tree is actually still balanced. Even though it's not as efficient as a perfectly balanced tree, it does still work well. And so what I'll do here is I'll say, okay, I want to prove some kind of inequality about this. So I'll say the worst number of nodes that you can pack in, it's actually going to be greater than 2 times n h minus 2, right? Because I know that n h minus 1 is greater than n h minus 2. So if I make this n h minus 2 and then I get rid of the 1, well, certainly this is going to be greater than that. Okay? All right, and the closed form expression for this is nh is greater than 2 to the h over 2. So now I can ask a similar question to what I asked with the perfectly balanced binary search tree, and I can say, okay, if you have so many nodes, what would the height of the AVL tree have to be in the worst case to accommodate that? So in other words, I'll solve for h here. And what I get is that, okay, if I take the log base 2 of both sides here, I get that h over 2 is less than an h, log base 2 of an h, or the number of nodes that you have. And so then I multiply both sides by 2, and I get that the height is less than 2 log n. Okay? So before I had that the height was, in a perfectly balanced binary search tree, I had that the height was equal to basically log base 2 of n minus 1. So actually even a little better than that. But here it grows as a factor 2 times the log base 2 of n. But guess what? If we're talking big O notation, this is still log n. So we say, therefore, the height is still big O of log n in an AVL tree. And that's awesome, because that means that if we can do this, we can be a little bit more permissive, and we'll end up with a tree where we can still do add, contains, and remove in logarithmic time. So let me tell you how to maintain an AVL tree even as you add and remove stuff from it and it becomes unbalanced. So let's suppose I had this tree here, and we'll say it's AVL. Without loss of generality, I'll say it's maybe heavier on the left side, so I'll say the height here with respect to x is h plus 1, and then I'll say that the height over here is h. So I'll do this, I'll assume that they're just like that, so that if I go ahead and I add something to the left, and let's say that it ends up down here, then suddenly this actually turns into an h plus 2 height subtree, right? So if I add something here, it's going to turn into an h plus 2 height subtree. And now I see that I am not AVL anymore because I've violated the balance condition at the root. So now this is h plus 2. I mean, everything, within A I'm AVL, within B I'm AVL, within C I'm AVL. But I'm saying suddenly here I'm not AVL anymore at y. And I need to fix that. And so what I can do is actually do a tree rotation. And if I do a clockwise tree rotation about the root y here, I can seesaw this C down. That's fine because C is lighter. That's going to get an additional height of plus 1. B will stay the same, but it'll flip over to the other side. And then A will move up. So it's kind of like the seesaw goes down. C gets heavier, but A gets lighter. A goes up a little bit. So let me do that real quick, and I'll show you on the other side. All right, so there it is. And if we look at the before and after, again, what happens is that A swings up, B swings to the other side, but stays at the same height, and C comes down. So C, which was at a height of H, now with respect to this node that's come down, is a height of H plus 1. A actually moved up to where X was, the root of A. So that has a height of H plus 1. And B is going to have a height you know, if I go down from y to the leaves of b, it's going to have a height of at most h plus 1. It could have a height of h because this is AVL. Could have been that b was a little bit one shorter than a. But anyway, this so now we can see that this tree is AVL. Okay, if you follow it all the way through. So that was great. That seemed to fix the problem. But there is something else that can happen. And what can happen is when I go to add, yeah, so let's say that I started off just like I did before, where, yes, I'll copy this whole thing here. And so the left side is going to have a height of h plus 1 now. But this time, when I add the node, it actually ends up in this subtree here. And let's assume also that this subtree was the same height as the subtree. Okay, it could have been that this was one shorter and then that wouldn't cause a problem. But let's assume that A and B are both height h. Okay, that's what's going to cause a problem. Because now the height of this subtree will be h plus 1, or sorry, h plus 2 here. So if I assume A and B are the same height, this is going to be kind of bad news because now I can't fix this by doing the same clockwise rotation. So if this is height h plus 2, remember the before and the after doesn't actually change the height of this B subtree here, right? So B actually stayed at the same height that it was. It just swung to the other side. So a clockwise rotation there is not going to cut it. But what I can do instead is I can fix up this left part of the tree first and reduce it to this case. And I'm going to do that actually by doing a counterclockwise rotation about x. So let me break B down actually into two trees. And so I'll consider the left subtree of B. I'll call this BL. And then I'll consider the right subtree of B, which I'll call BR. So let me just get that set up there. All right, so here's what we end up with. So let me assume that BL and BR both achieve a height of h plus 2. That's kind of the worst case. If I can deal with that, then I'll be good. So let me now do a counterclockwise rotation about x. Okay, so when I do that, here's what I end up with. And what you see has happened is this heavy BL has switched over here and A has moved down by 1. So I've suddenly moved over the heavy part to the left side. And now if I look at this tree here holistically, so let me draw a little triangle around this to kind of group these together. If I look at this holistically, then I can see now I'm back to the original case, right? So now I'm back to the case where I had something heavier on the left here. And so now I can just do a counterclockwise, or I could do a clockwise rotation about the root, and I'll be able to fix this. So actually, let me give this node here a name. This is W. I'll call that W on the other side too. So now I'm going to do a clockwise rotation about the root, and I will be able to end up back in the situation I was before. So let me just do that real quick. Okay, so once we've done that, this whole subtree moves up by 1, BR switches to the other side, and then C moves down by 1 like a seesaw. And now we're in this situation where everything is height h plus 1. And so it's balanced. By the same reasoning before. But we had to, in this case, we had to reduce it to being heavy on the left in order to fix it up. So that was actually a two-step process. All right, so next what I'm going to have you do is implement this in code in Lab 6. And so once you do that, you'll see this nice pattern where if you start adding stuff and then you rebalance when necessary, see that just rotation happened there, you'll always be AVL and you'll always stay balanced. So I can add a bunch of stuff in any order, it doesn't matter, and I just keep fixing this up. and it stays balanced. And all you got to do is just every time you add something new, you update the heights, and then you follow these rules, which, I gave you the one side of it. So I said, okay, if, the right ends up being lighter than the left when you add something, what you got to do is check and say, okay, is the right part of it heavier than the left part? So that's that. So if left dot right has a height that's greater than left dot left, then do that counterclockwise rotation about left, and then do the clockwise rotation about the root y. And so yeah, it's just this extra if statement in here just to see if you need to make it left heavy, and then go. And then it's the same thing on the other side. Everything is symmetric over there. So this is what it boils down to in pseudocode, basically. And so that's what you're going to do. And so we'll just worry about add for now, but I mean remove is similar. You could remove a node, and suddenly one of them becomes too short, and so then you have to fix that too. But in this lab, I'll just focus on add, and then we'll have a binary search tree which you can add things in any order. You don't have to be fancy and add them in this really special order to get a balanced tree. You can get a tree that's AVL, and that we know that within a factor of 2, and actually even a little bit better than that, slightly tighter bound, closer to Fibonacci number, we'll know that it's within that factor of the height of a perfectly balanced tree. And so we could say all the operations are log in time. So good luck with the lab, and as usual, ask questions on Discord.